Hello and welcome back to Network Steganography. This is an extended slide coverage for Chapter 7a. So in the first video for Chapter 7, I was not explaining all the slides that you find in the slide deck. So in this video, I will discuss the remaining slides. So I spoke about in the other video already about the problem of the small false positive rate that can lead to a problem during the practical application of detection methods, because if we have a high number of data sets, then or for instance network flows that we analyze, and then in this case have a false positive rate of even just 1%, it might result in still many false positives that we need to investigate by hand. So this can be impractical. 1% is of course a pretty low false positive rate for detector. Many approaches are rather at 5%. What is also new is this Warden's categorization. So we proposed a new taxonomy, and I thought, well, this is good to include in this class because it gives you an overview of all types of wardens that are there. So as you can see, there are three main ways to describe a warden. First over the behavior, then over structure and localization, and thirdly over its knowledge. You already know that a warden's behavior can be active or passive. You know what a stateful inspection and stateless inspection is. It's, for instance, traffic normalization that is considering the state of a flow, or then it would be stateful. If it would be stateless, it would only analyze data on a per packet basis and forget what the warden has seen previously. It can be a proactive or reactive approach. So that means that we can either react in the sense that if the warden spots some steganographic communication, it can actively influence this communication. Alternatively, it could be proactive in the sense that it tries to prevent the covert communication without detecting it, so it can also act blindly. By the way, all these categorizations here are described in a paper. I linked the preprint here because it's freely accessible and it already explains the taxonomy quite well. The final document is behind paywall of Elsevier, so if you want to read the final version, you need access to Elsevier, but you don't need this for this class. The warden can either become aware and document a steganographic communication. It can also eliminate or limit it. It can detect and audit it. Of course, these can be the hybrid solutions are feasible, so there is no reason why a warden would not be able to detect and then eliminate a traffic in some cases at least. And a warden can be static and dynamic. Static warden applies always the same heuristics, rule set, and algorithms, and a dynamic one can modify its own behavior over time. We will see one example for dynamic warden in chapter 7b. So then there is the structure and localization part. A warden can be either centralized or distributed, so it either has one point of observation or multiple that work jointly, which can be advantageous in case you have a distributed system such as a network and multiple hops where you place a warden, and these warden nodes collaborate so that their shared knowledge is combined in the a detection, elimination, or, for instance, limitation process. The warden can, moreover, operate locally on one hop, or it can be one focusing on the network environment. Next, there is the differentiation between local state level oblivious and state level omniscient warden. The taxonomy for these three aspects is derived by an analogy from the sensors classification used in evaluating censorship circumvention systems. There is a reference to this paper that was used to derive this classification from in the linked FGCS paper. Reference number 30 in the final paper version published in the journal. So a local warden controls at most a few network devices, is able to monitor only a small number of connections, and its computational and or storage resources are limited. We can further divide this into a local host or local network warden. Then there's the state level oblivious warden, and that one has access to a vast number of devices spread geographically, but it cannot keep network traces for a long time, nor can it perform complex traffic analysis, which is due to limited computational or storage resources. It can perform, for instance, the packet inspection, but can inflict it on short observations of network traffic. That means single packets and not too many connections or flows. And finally, the state level omniscient warden controls geographically dispersed devices, can perform a variety of complex traffic analysis, and store vast amounts of the intercepted traffic. This is how we describe structure and localization of a warden. And finally, we also have the knowledge of warden, which can be divided into two main aspects, which is a covert communication and network topology. So let's start with the small one, the network topology. The warden can either be aware of the network topology or not. If it's aware of the network topology, it can, for instance, I will also give one example here in chapter 7b then, for the network aware active warden. So it can, for instance, be aware of the network structure, and then it knows how many hops one node is located away from another hop. So if you want to evaluate whether a packet reaches the destination and look at the IP version 4 time to live field, or the hop count and hop limit fields of other protocols like IP version 6 or BACnet, then the warden could say, well, this packet will anyway not reach the receiver, so I can drop it without having any influence on the network traffic, on legitimate traffic, because the legitimate destination would anyway not be reached by this packet. So finally, the covert communication can be described over the covert channel representation and hiding technique internals. Let's start with the covert channel representation. So the warden can first be unaware of the presence of the information hiding technique, but suspects that some covert communication could take place. In that case, the warden has no knowledge of the specifics of the information hiding technique. And in result, only normalization rules based on the previous experience can be applied in the hope that they will be sufficient to infer or destroy the covert channel. That means the warden would act blindly. Secondly, the warden can be only aware of the presence of the steganographic method, but it possesses no knowledge about the specifics of the technique used to create the covert channel. In this case, it tries to influence its operation and semantics randomly, for instance, by injecting false data or erasing some packets. This is also a form of a blind attack. Next, the warden can be partially aware of the presence and the specifics of the information hiding technique used to perform the covert communication. The knowledge that the warden has can be related to syntax or semantics of the method, and it can be efficiently utilized to inject targeted, legitimately appearing but falsified data to infer with or to eliminate the covert channel. So this would allow the conduction of a targeted attack. And finally, the warden can be fully aware of the presence and the specifics of the technique used, and even the hidden data scenario in which the communication takes place. In that case, the warden can try targeted attacks to exploit weaknesses in the network covert channel design. If such weaknesses are identified, the warden has the largest possible control. So that means it can not only destroy the covert channel efficiently, but it can also eavesdrop or influence it, for instance, by impersonating one of the communication sites. This is the most sophisticated form here of the warden that allows highly targeted attacks. And finally, by the way, these 4 categories are derived also by the paper from Kawa et al. That is shown here on the side. But in that paper, the categorization was actually made for covert channel internal control protocols and not for wardens. So it was basically derived from this categorization. So finally, information hiding internals. One can be aware of details of the embedding process and the extracting process and of the control protocol. I said already that in the other video that we can differentiate between detection, limitation, prevention, and elimination. Essentially, I mean, there's also auditing and so on. And however, in this class, I differentiate between especially these 3 cases. So there are a few methods that I did not show in the previous video that I want to explain now. I added them recently because I believe that it's important to understand some classical approaches and to get a broader perspective of these methods that are available. So for elimination, I cover some classical examples: blind, writeup, and upwards channel. I already explained traffic normalization in the other video. For detection, I also explained several approaches and will detail a few more. And for limitation, I also added some standard approaches that I want to explain in this video. First, however, I want to highlight the concept of the minimal requisite fidelity, MRF, that was introduced in 2003 by Fisk et al. So the concept is, or the idea is to have a measure of distortion introduced to a potential steganographic carrier in order to counter covert communication, while still providing legitimate end-user acceptance of the communication. So what this means is we have, in the end, a trade-off. I mean, we can block all communication, and then we block also all covert channels, most likely, which is good from a security perspective, but horrible from a usability perspective. So we would not provide legitimate end-user acceptance in that case. This is similar to steganographic cost, but it focuses on countermeasures. Now, I want to highlight the different elimination, detection, and limitation approaches that were not covered in the other video, and I want to start with elimination approaches. The first one is a blind write-up, and this is essentially the most simple protocol you can imagine. By the way, these approaches here are described in the context of multi-level security, for instance, using the BLP model, Bella-Padula model that I explained in earlier chapters. So what you have here is a low and a high system. So for instance, a secret level system and a top secret level system. And the blind write-up allows only communication from low to high and blocks all communications from high to low. So this eliminates all write-downs and also all back channels for the read-up. So you just have no covert communication channels feasible anymore. But you also don't have any acknowledgements or reliability features. So it's not a practically applicable approach, more a theoretical one. By the way, it's also called sometimes a one-way link. Then there's the upwards channel, which is essentially the same idea like blind write-up, but it contains a buffer so that at least a bit of reliability is achieved. So if low sends too fast, then the upwards channel can cache some data, some packets in its buffer, which are then forwarded. However, the buffer can also become full, and then you still have reliability issues. So it's not that reliability is always provided, this is just a limitation of the problem. I also want to add a few aspects to detection approaches. So in general, we can perform detection using simple approaches like IDS signatures. For instance, if we want to detect ping tunnel packets, ping tunnel is the tool that I described earlier in chapter 4, where each ICMP echo payload packet contains this magic byte. So we could simply, and this is also done by, for instance, the Snort IDS, search every ICMP echo packet that we see and look into every payload and check whether the magic byte is there. And if we find it, then we say, hey, alert, there is a covert channel. I will exclude these signatures because they are highly specific and not so interesting from a scientific perspective. I will discuss a few more heuristics. I already explained the compressibility score, the approach by Berg et al., epsilon similarity, but I will highlight a few more just to give you more examples. And by the way, if you are interested in even more countermeasures or heuristics, then see our book Network Information Hiding in Communication Networks, where we cover some additional approaches like the Kolmogorov-Smirnov test, the KL distance, and so on. And what I also will exclude here are machine learning based approaches, because machine learning is not within the scope in this class, and I don't want to make machine learning essentials a mandatory a must-have for this class. So I want students to accomplish this class without having prior knowledge on machine learning. However, there are certain approaches described in literature, like decision trees and so on, that can be used. We also used them in the past quite a lot, different approaches to detect covert channels. But if you understand the essential approaches, especially the heuristics, then you can also use them as machine learning features. So something like the compressibility score or the epsilon similarity, though not being perfect, they can be combined as features in a more complex system. So a very simple approach is the Jacquard similarity. So you just have two sets, A and B, and this is a measure of the similarity. So for instance, you check whether, so both sets could, for instance, contain packet sizes of flows or interarrival times, and you check whether, for instance, let's assume A is one recorded covert channel's traffic characteristics, and B is the current traffic you observe, and you want to see how similar they are. And you could also use this, of course, as a machine learning metric. I discussed the approach of Berg et al. In the previous video, and also the one on the epsilon similarity and the compressibility score. By the way, we made quite some we had quite some success when we applied both approaches to different types of covert channels using countermeasure variation. They do not always work well, but if you combine them again as machine learning features, then you get pretty satisfying results. Another approach that I want to highlight, at least briefly, is the regularity measure that was used by Cabot et al. So the goal there is to determine whether the delays between packets are relatively constant or not. And as you know, a covert channel that, for instance, uses two different symbols always has a constant or usually constant delays because it has very few different delays. If you have one delay of 1 second and another delay of 2 seconds, then these patterns are also, of course, detectable with the other approaches described by Cabot et al., but also here. So this is essentially based on the standard deviation. As we will see in chapter 8, where we did a replication study for, in that case, for the compressibility metric by Cabot et al., we will see that such heuristics highly depend on certain traffic characteristics and also the medium used. So whether you transfer the data over Ethernet or over a long distance internet connection, and whether it's an HTTP download or whether it's an email exchange or chat protocol makes a big difference. And also the implementation of the protocol actually makes a big difference. This is something I won't discuss in chapter 8, I think, but imagine a protocol that performs polling. A legitimate polling protocol would have similar characteristics to a covert timing channel using interpacket gaps, because you would poll some status, for instance, in a regular interval, let's assume every 2 seconds or so. So that would look almost perfect for a covert channel. In that sense, such heuristics are not very useful. And I want to show just another trivial one here. Trivial does not mean bad. Actually, it works pretty well. It was designed by Sebastian Zillian, one of my students. And this is a heuristic for detecting the artificial reconnections channel in Wi-Fi networks that I discussed in chapter 5 on hiding patterns. So I assume you're still familiar with this pattern. If not, have a look into chapter 5. So the idea essentially is you have a Wi-Fi hotspot and clients connected to the, or nodes connected to the Wi-Fi hotspot, and the covert sender triggers their reconnections artificially, either directly controls them or has to perform some deauthentication attack to reconnect them. So the idea here is a sliding window approach where we sniff data for some interval. Here it's L seconds. Then we count the number of deauthentication frames during that time frame during that window, and if the number is above or equals some threshold, then we raise an alarm and say, okay, this is a covert channel. As you can see, oldest end seconds of frames are then discarded and some new traffic is recorded or sniffed. So this is the implementation of the sliding window. So for method 1, the ROC chart, ROC as receiver operator characteristics, is perfect. So we have a false positive rate linked to a true positive rate of 100%, while the false positive rate is 0, which is perfect. For method 2, it's not the same, but almost perfect, as you can see here. So it's the area under curve is 0.99 or something, so it's really good. Now I want to add a few words on traditional limitation approaches. So they were designed mostly for timing channels in the multi-level security or Bella Padula context. Again, refer to chapter 1 if you don't remember the concept behind this. So so these approaches are similar to blind write-up, aka one-way link. So we have here the ACK channel, which is the idea here is that the low system is allowed to transfer all data to the high process, so like the blind Writeup, but high is only allowed to acknowledge data. That means we have reliability, and this still leaves room for timing channel because high can send X or not, and this of course allows an attack where a one-bit channel is feasible, or even the rate of acknowledgements could be modulated. The store and forward protocol, SAFP, is similar, so we have a low system that transfers data to the high system. And in order to achieve a reliable communication, high must send X to low, so this is like the ACK channel. But the SAFP is a gateway that sits in between them and immediately acknowledges every message from low before it forwards the message to high. So we eliminate the direct acknowledgements from high to low that we have in case of the ACK channel. Problem is the SAFP is a buffer, and the buffer can overflow or get full if the high system does not send acknowledgements, and this way the SAFP gateway also has the problem of not being able to acknowledge data from low because the buffer is full. So there would still be an indirect timing channel feasible. And finally, the pump. There are different approaches like the network pump and the quantized pump. This is again like the SAFP, but it caches the data from low to high in a buffer that it flushes entirely at some point in time in regular intervals. So it caches all the messages and then sends all the messages to high in one flush. And X from high to low are sent over the pump, but the pump adds a random delay to the acknowledgements before forwarding them to low. So none of these channels eliminates the covert channel entirely. All of them are limitation approaches. And as you can see here in this overview, it's from 2015, state of the art back then. So as you can see, sometimes traffic normalization can be applied to eliminate a pattern, while it can only be used to limit other patterns. NPRC is the network pump and related concept, so it's what I just discussed on the previous slide. And as you can see, timing channels can usually only be limited. So for this class in Hagen, these slides where I experimented with the C45 decision tree classifier are not relevant for the exam. It's just to show you that an unpruned tree can improve the performance over a heuristic, but then it's highly tailored for specific traffic characteristics, so this is not what I recommend to do. It's just to show that there's still some improvement potential over some heuristics if you apply machine learning methods the right way. However, I don't want to discuss pruning and additional aspects such as overfitting in this course. So this is all that I wanted to add to this chapter. Thank you very much for your kind attention, and we see us in chapter 7b.